This is Dr. Reed. Welcome to the Chapter 13 analysis video on chi-square and proportions. In this video, I will cover the following. Review, data, variables, and levels of measurement. Chi-square overview, computation, sampling distribution, and classification. Chi-square test of independence. Chi-square test of homogeneity. Chi-square goodness of fit test, and I'll end with a summary. Review of variables and levels of measurement. So there are two main types of data. First is the quantitative category. This type of data is numerical in nature, and you use statistical analysis for this type of data. The second main type, if you look down at the bottom of the slide here, is qualitative data. This is non-numerical data, and it is used in qualitative studies, and you use a thematic type of analysis for this type of data. So the qualitative data is descriptive and non-numerical in nature, such as text, audio, video, and images. So for this course, though, we've been mainly talking about the quantitative. So let's go back up to the quantitative and talk about that. So there are two main types of quantitative data. One is categorical, and the other one is numerical, as shown here with my pointer. So let's talk about the categorical first. So categorical data can be looked at as categorical variables, and in this case the data is in categories, or it's grouped into categories, then assigned values by the researcher. The data are nominal or ordinal level. Under the categorical, there are two main types. There's a nominal variable, where categories are without rank or order, such as hair color, gender, or a yes-no response. The other categorical variable is the ordinal type. And in this case, the categories have order. So it's categories with order, such as education level or any data that's obtained through a Likert scale format response, such as commonly used in surveys. Then the other main type of quantitative data are numerical variables. In this case, data counted or measured numerically and are in the interval or ratio level of measurement. And there are two main types of numerical variables. One is discrete. This is data that's obtained by counting, such as heart rate or number of children. And in this case, in a discrete numerical variable, you have each value is in its own right. In other words, you can't have values that are fractions or decimals. They're discrete in nature. Again, heart rate and number of children would be good examples of that. And then the other type is the continuous. So it's quantitative, it's numerical, and it's a continuous type of variable. And this type is obtained by measuring, and type can take any value within a range to include fractions and decimals. And so examples of that might be something like height, weight, or time are good examples of numerical continuous variables. And so what we're going to be doing is looking at the chi-square statistic. And so let's put that with the chi-square. So the chi-square statistic is typically used to examine frequency counts for categorical variables at the nominal level. While means are used to summarize continuous variables, proportions and mode and median are used to summarize discrete variables or categorical variables at the nominal or ordinal level. For the chi-square, we will use proportions as summaries. A proportion is the count, rather than the sum, as for the mean, of a given value divided by the count of the total number of values. Let's do a chi-square overview now. Chi-square tests analyze response frequencies, abbreviated FS, by comparing the observed O frequencies or responses of your study to expected E frequencies under random sampling. Question: do O frequencies provide probability or confidence interval evidence against the notion that O and E frequencies are the same? That's the question we're going to be asking and attempting to answer with the chi-square test and proportion. The chi-square is a non-parametric statistic, meaning that no distribution assumptions are required. Note, with large samples, greater than or equal to 500, for example, even very small O to E frequency differences will indicate probability evidence against the null, which we're going to be talking about more later. For example, you might want to examine the frequency of absences between boys and girls at 2 elementary schools. A common visual setup for chi-square tests is the 2x2 table, often called a 2x2 contingency table. The chi-square for the 2x2 table has 1 degree of freedom. The degree of freedom is based on the number of table cells and is equal to the number of rows minus 1 times the number of columns minus 1. So, for the 2x2 table, you have 2 minus 1 times 2 minus 1, which is equal to 1 times 1, which is equal to 1. So for the 2x2 table, we're always dealing with 1 degree of freedom. And for that 1 degree of freedom, there's a specific critical value for the chi-square test that will always be the same, which we'll talk about in the next couple of slides. So let's look at if you look over on the right here, you can get a little picture then of maybe this example. And so here's your 2x2 table with the 4 cells of each response category. And so we have a variable or group over here for on the side here that could be labeled absences, boys, girls. And then you have up on top here the school variable, and I just came up with a couple names of different elementary schools like Springville and Pinewood, for example. And so you have these 4 cells to separate out the possible combinations of the responses. So in this first cell here, which is typically labeled cell A, we have the absences for boys at the Springville Elementary School. And in this cell here, which is typically labeled as cell B, you have the responses for boys at Pinewood Elementary. Likewise, in cell C, we have the girls' absences at Springville. And then in cell D, we have the girls' frequency of absence at Pinewood Elementary. So this is the typical kind of setup that we would look at, and it's sort of a visual heuristic so that you can get a sense of what your data look like. So the procedure computes a value, that is, the value of the chi-square statistic that represents an index of the difference between what you observe and what would be expected by random chance. The O frequencies, or the observed frequencies, are typically the ones that are shown in this table down here below. Oftentimes you see computer programs put both the observed and expected frequency in each of the 4 cells, but usually you see just the observed frequencies. Now let's move on to the computation of the chi-square statistic. So this is, I'm going to go through this just so you can get a better idea of some of the terminology that's used and some of the symbols. And it's nice to kind of go through a computation at least once so you can see how it's done. So if you look over here on the right, I have that 2x2 contingency table set up with the various labels that you would use if you were doing such an analysis. So we have, for the rows here, you can have a variable or a group. This would be sort of your label for your row 1 here and your label for your row 2. And then there's also, as you saw on the prior slide, there's a variable for the columns. So C1 is column 1 and C2 is column 2. And then for each of the 4 cells, you have your cell A, which is your row 1, column 1 responses. Your cell B, which is your row 1, column 2 responses. And cell C, which is your row 2, column 1 responses. And cell D, which is your row 2, column 2 responses. Then you can also look at the table in terms of the row itself. So for example, you can look at row 1 across the 2 columns, and the R1T, that stands for the row 1 total of responses. So if you were to add the responses in cell A and cell B, you would have a row 1 total. Likewise, you can do the same thing with cells C and D to get a row 2 total. And because you can do the rows, you can also do the columns. So if we add the responses in column 1, that would be A plus C. That'll give me my column 1 totals. And for column 2, of course, you'd have the B and D responses added together. And then oftentimes what you see is down here in the lower right-hand corner would be the total of all 4 cells, which is also equal to the total of the row 1 and row 2 totals, and this column 1, column 2 total. So if you add up the row 1 total and the row 2 total, you add those 2 values together, you get the total response. And that should also, the total response here should also be equal to the column 1, column 2 totals. And so as a check, you want to make sure that everything kind of adds up together. So let's take a look at an example to see how this is calculated out. So if you focus your attention over here on the left, we'll start here and do an example and calculate one through for you. Let's say you're interested in looking at the detentions between boys and girls at your school. So we have a group here, and I'm labeling that gender. We have boys and girls. So boys row 1, girls row 2. And then in the columns, we have this categorical variable at the nominal level of yes, no for detentions. So you can see that there. And what you see in the 4 cells are the observed responses, or the observed number of detentions that were logged at your school between boys and girls. So for the boys, we have 15 yes, 24 no. For the girls, we have 11 yes and 30 no. And then you can look on the what's called, if you look to the outside of the contingency table, you have these values here. You have the row 1 total, the row 2 total, column 1 total, and the column 2 total. And oftentimes these values out here outside of the actual observed responses, these are called the marginal values of the table. So 39 is the row 1 marginal, 41 is the row 2 marginal, for example. So everything adds up because you can see that 15 and 24 equals 39, 11 and 30 equals 41, and then 39 plus 41 is equal to 80. But as a check, you can also see that 26 plus 54, which are the column totals, 26 plus 54 is also equal to 80. So now you're ready to do the calculations here. So the first step in the calculation is to calculate the expected frequencies based on what we observed in this first table. So if you shift your attention to the middle box here, we can calculate these expected frequencies. So how is that done? In the first box here, we have 12.7. So how that's calculated is that 12.7 right there is equal to the following. It's equal to the row 1 total times the column 1 total divided by the entire total for the table. So this would be, this cell here corresponds to cell A. So to get this value here, which comes out to be 12.7, you have cell A over here, and you take the corresponding marginals for that cell. In this case, it would be the row 1 marginal times the column 1 marginal, because row 1 and column 1, that's where this cell A is located. So you multiply those two values together and divide by the total. So 39 times 26 divided by 80 is equal to 12.7. And so you essentially do that for the remainder of the cells to obtain the expected frequencies. So for cell B, it would be the corresponding marginals are row 1 and column 2. So in that case, we would take 39 times 54. So from over here, 39 times 54, because you're looking at this cell here. So 39 times 54 divided by 80, and that is equal to 26.3. So for cell C, we would take 41 times 26 divided by 80. And that gives you 13.3. And finally, for cell D, which corresponds to the row 2, column 2 marginals, you take 41 times 54 divided by 80, and you get 27.7. Then the next thing you do is move to the table over here on the right and calculate the expected frequency, which we just calculated, minus each corresponding observed frequency, and then square it. So for example, the 5.3 in cell A would be equal to the 12.7 minus the 15 squared. And you just do that then for each of the other remaining 3 cells. In this case, it comes out to be roughly 5.3 for each cell. Then the next step, if you look down here in the lower left, we have a table that is the observed minus the expected minus the observed squared. Each of those values are divided by the corresponding expected value to obtain each of the values that you see in this table. So for example, in cell A, the 0.42 would be equal to the 5.3 value divided by 12.7 that you see up here. And then you just simply do that for each of the remaining 3 cells. And now you're essentially ready to calculate the statistic. So the actual chi-square statistic then is equal to simply the sum of those 4 corresponding cell values in the table that you see over here on the left. So you add those together, and we end up with a chi-square statistic for this example analysis of 1.21. That's the value. So that's the computation. And again, of course, the computer will be doing the computation for you, but it's nice to kind of run through that once so you at least know how that's done. Now let's take a look at the chi-square sampling distribution. This will give us a look at what we need to have for our observed chi-square statistic relative to the critical value for the chi-square statistic at 1 degree of freedom. So let's create that. So the goal here is to create the sampling distribution for the chi-square at 1 degree of freedom. So to do that, you can tell a computer to randomly select values from a standard normal population having a mean of 0 and a variance of 1 to form a large sample. For example, n equals 100,000 values. Then square all the sample values. The histogram of these values is the chi-squared statistic at 1 degree of freedom. It's the sampling distribution for that statistic. So let's take a look at a picture for that. So there's our population with mean of 0 and variance of 1. In this case, of course, it would be the standard deviation would be equal to 1. Okay, so randomly select a value, square it, and plot it, repeat 100,000 times, and you end up with a distribution that looks like you see with this blue line right here. Probability is on the y-axis with the chi-square value on the x-axis. To show a discrepancy between O and observed frequencies, your chi-square should be greater than or equal to the critical chi-square at 1 degree of freedom of 3.84. So for the 2x2 table that we are using throughout this entire presentation, the critical value will always be 3.84. So any 2x2 table for a chi-square analysis, the critical value for the analysis is 3.84. So the value of 3.84 occurs 5% of the time in random sampling. That is, if your observed chi-square is greater than or equal to 3.84, you can claim probability evidence against the null at the 0.05 level. So that looks like this. So along this x-axis, our value of 3.84 is right about there. And so if you go up to the sampling distribution curve, okay, and then go over to the probability, you can see that the value of 3.84 occurs 5% of the time in the random sampling process. So essentially, as you go farther out on the x-axis, larger values of the chi-square at 1 degree of freedom occur less and less frequency, less and less frequently, sorry. And so your observed chi-square needs to be equal to or greater than this critical value of 3.84 in order for you to claim a statistical discrepancy between the observed and expected frequencies. So here, anything at or above the 3.84, we can call that sort of the zone of probability evidence against the null. So if your observed chi-square value is in this zone, i.e. greater than or equal to 3.84, we have license to claim probability evidence against the null hypothesis, which the null hypothesis states that the observed and expected frequencies are equal. Let's move on now to the chi-square classification. So now we're getting into the methodological part of the presentation here. So these chi-square tests, there are several different types. There's two of them that use a two-way table and one that uses a single row table. So let's start at the top and look at the two types that use the two-way table. First one I will discuss is the chi-square test of independence, TOI, test of independence. In this scenario, one group was sampled and two variables created. Each person is classified on the two variables. For example, variable 1, gender, male, female, and variable 2, smoking, yes, no. Your question is, are the two variables related with inference to the population? In other words, are the two variables related at the population level? And so in this scenario, your research plan is to sample from a population of people that includes both males and females. Each person then that was sampled would answer two questions on a survey, for example. One, are you male or female? And two, do you smoke or do you not smoke? That type of setup gives you the two variables for your 2x2 table, and the question that you have is, are those two variables related at the population level? If that is the plan and question for your research, then you would be using the chi-square test of independence. So the null hypothesis for this one is that there is no relation or very little relationship between the two categorical variables. Let's move on to the second one. This would be the chi-square test of homogeneity. In this case, two groups are sampled and one variable is created. Each person is classified on the one variable. For example, group 1 males on variable 1, smoking, yes, no, and group 2 females on variable 1, smoking, yes, no. The question is, are the frequency responses of each group similar on the categorical variable of interest, or are they different? So in this case, unlike the test of independence, you purposefully sampled from a group of males or a population of males only. And then each male in that sample answered the question, do you smoke or not? Then you had also purposely sampled from a population of females only. And then each female in that sample from the female only population answered the question, do you smoke or not? And your question is, are the frequency responses of each group similar on the categorical variable of interest, with inference to the population, of course. So you can see that how the data were sampled is very important as to which question you have and which type of test you're going to use. The null for the test of homogeneity is the frequency responses of each group are the same or very similar on the categorical variable. And then the last one is one in which simply a one-way or single row table is used. And this one's called the chi-square goodness of fit. So for each one of these three types of tests, a chi-square statistic is generated. It's just that it's interpreted differently according to which type of test you're using. So for the chi-square goodness of fit test, we have a situation where one group is sampled and one variable is created. Each person is classified on the one variable. For example, females on variable 1, smoking, yes, no. And in this case, your question is, are the frequency responses of the group that you have, your sample, are those responses consistent with a known or theoretical population frequency? So in this case, you're comparing your sample to a known population frequency to see if your data are consistent with that known population frequency. That's why they call it the goodness of fit test. So oftentimes in this one, you're looking to see, in fact, or you're maybe wanting to see if your data are in fact similar to the frequency responses in the standard population rather than being different. So the null here is the frequency responses of the group are the same or very similar as the known population frequency. And so in this case, you're actually wanting to maybe have your data be consistent with the null rather than wanting to have evidence against the null. So those are the three tests that are done. And what I'm going to do now is we're going to go through each one of those and give you an example and an interpretation. So let's start with the chi-square test of independence. In this one, you have one sample and two variables. Each person in the sample responded to two questions. And the responses on those two questions create the two variables for your 2 by 2 table. So it would look something like this. There's your population, there's your sample, and we've created variable 1 and variable 2 for our 2 by 2 table. So TOI, one sample, two variables. Now on this one, before I go to the actual example, we have to have some ability to interpret the outcome here, and that has to do with some terminology in terms of what it means when two variables are either dependent or not dependent upon one another. So let's look at an example of that first, and then we'll go to the actual numerical example. So for the test of independence, classify subjects on two variables. Example, smoking yes, no, and gender male, female. Question, are the two variables related to one another at the population level? If not, they are independent, indicating that knowledge of which category a person is in on one variable gives you no real indication of what category they are in on the other variable. Example, so there's the setup and some fictitious data. We have males and females for the rows, smoking yes, no for the columns. So now take a look at this data here. We have males 25, 26, females 24, 27. If you know a participant is male or female, based on this data right here, can you predict with any confidence whether they smoke or not? The answer is you cannot. Therefore, the variables are independent of one another, meaning there's no relationship between gender and smoking. What about this? Take a look over here on the right a little bit more. Same variables with different numbers. We have males smoking 5, not smoking 46. Females smoking 44, 7 report no. Now, looking at this data, if you know a participant is male or female, can you predict with any confidence whether or not they smoke? The answer is yes, you can. In other words, if you were to bet on males, randomly pick a male from the sample, would you bet that they smoke or that they don't smoke? Well, you're going to bet that they don't smoke. On the other hand, if it were females, would you bet that they smoke or they don't smoke? You would bet that they do smoke, given the numbers in the table. And because you can do that, the variables are therefore dependent. Whether you smoke or not depends largely on whether you're male or female. In this case, there is a relation. There's a relation between gender and smoking. And so that I'm presenting this because it has something to do with if you're wanting to know this type of question using a 2x2 chi-square analysis, if you want to know if the two variables are related or not, you have to determine whether or not we're dealing with two variables that are resultingly independent of one another, meaning there's no relationship, like over here on the left, or whether there is a dependency between gender and smoking, like we have over here on the right. In fact, they are related because we can predict with pretty good confidence whether or not a person smokes given their gender being either male or female. What about the effect size? We haven't mentioned that yet, but the effect size then we want to make sure we include an effect size for the analysis. So the effect size for the test of independence, the chi-square statistic itself addresses the issue of whether there may be an association between the variables. However, the chi-square does not indicate the strength of the association in the population. This is the job of the effect size. And for this test of independence, a common effect size that can be used is called the phi coefficient. The Greek letter phi there. The phi coefficient measures the strength of the 2-by-2 association in the population under conditions where the researcher chose a single sample, as in the TOI, and not the row samples separately, as in the TOH. So we're going to use the we're going to use the phi coefficient for the effect size for the example. So let's move to the example. Oh, and by the way, Jamovi can compute some of these effect sizes for you and gives you several other options as well. So let's do a TOI example, test of independence. You obtain a small random sample of 40 students at your junior high to test if there is a relation between gender and absence from school. Based on your sampling and your question, you're going to use the test of independence. So I went into Jamovi, so we have some screenshots of that now. So first thing is, look over on the left. So the data would look something like this here. The first column there is the gender, and the second column is the absence. So in the first column, we have the gender, boy or girl, and in the second column, we have the response, or the data that was obtained, either absence no or absence yes, for each boy and each girl. So for this one, we're not going to use ESCI, but we can use frequencies under the analysis tab in Jamovi. And when you do that, you end up calling up this middle dialog box here, contingency tables, and then you just simply put the two variables over in the appropriate spots. So if you want gender as the rows, pull that over to the rows box, and then we want the absence status in the columns. You just put that over there, and you're essentially done. Then you can choose the statistic that you want. So if you go down here, you can see I just simply selected the chi-square statistic, and then also down below, it's not shown on the screen, you can also choose a different type of effect size, and that'll be the phi coefficient. So then you see the results over here on the right, which I'm going to talk about on the next slide or so. And then you can also see here at the bottom, it includes that phi coefficient effect size, which we can interpret. So here is the output from that. So I just copied and pasted the output. So if we look up at the top here, there's your variable 1 and your variable 2, gender and absence, and we have everything that we need. We have our observed responses in each of the 4 cells. So there's cell A, B, C, and D. There's the row marginal, second row marginal, first column marginal, second column marginal, and the total of 40. Everything adds up. And then the chi-square statistic analysis, we end up with a chi-square value of 0.08, 0.08. And if you make a note of that, that is well below the critical value of 3.84. We have 1 degree of freedom, and the probability value for that is 0.78. And then for the phi coefficient, we have a value of 0.05. And again, a phi coefficient is basically a Pearson's correlation coefficient between two categorical variables, each having two possible responses, which is what we have. And then Jamovi does not give you a confidence interval for the phi coefficient, but I was able to either go online or go in Excel and compute one for us. So this is the corresponding 95% confidence interval for the phi coefficient effect size. It ranges from minus 0.27 to 0.36, with a 0 indicating no relationship between the two variables whatsoever. And as you can see with this confidence interval and the actual value of the phi coefficient, that we're looking like there's no relationship here. In other words, the two variables are completely independent of one another. So let's interpret that, have that over here on the left. And we haven't done too much of that yet so far this semester, but one of the hardest things with the statistical analyses is to do the interpretations correctly. So let's go through an example interpretation. Assuming that the null is true, there's a good chance of obtaining a chi-square of 0.08 or greater. In other words, there's about because the p-value associated with that 0.08 is 0.78. So there's about a 78% chance, assuming the null is true, of obtaining a chi-square of 0.08 or greater. So that's a pretty good chance. This result, therefore, does not provide probability evidence against the null that says that the variables are independent. The phi coefficient is extremely low. It's 0.05. And the 95% confidence interval nearly straddles 0, minus 0.27 to a 0.36. The chi-square and associated probability evidence, along with the effect size results, are consistent with two variables that are independent of each other, meaning there's no relationship between them. The findings, therefore, point to the lack of an association between gender and frequency of absence at this school. However, the sample, if you make a note here, the sample is a little small. So if you look back up at the cells here, we don't have a lot of responses in each cell. In fact, I haven't mentioned this, but if you have 5 or less in a cell, this can make the analysis pretty unstable. And we're kind of down there a little bit. We have a total sample size of 40, which is relatively small if you attempt to divide that 40 up into 4 different compartments or cells. So if you go back down here, however, due to the small sample, some caution is probably warranted regarding inference to the general population of junior high school students because of the small sample. Now I also have here that I just pulled up this is my rendition or my going through the literature and making an attempt to come up with some standards for the Pearson correlation or the phi effect size correlation. And so based on my review of the literature, if you look at 0.05 to 0.09, that would be an extremely low correlation. 0.1 to 0.19, very low. 0.2 to 0.29, low, etc. Going all the way down. 0.7 to 0.79 is high. 0.8 to 0.89, very high. 0.95 to 0.99 is extremely high. Okay. So, and I have a little bit of, I'm still kind of working on this a little bit. You can see that the values of 0.9 to 0.94 are not included in here. But at any rate, you can see I have somewhat of a scale there that can be used. For this example here, we see that we have a very low correlation. So this is my rendition of a Likert scale approach to interpreting the Pearson R or phi coefficient, giving these verbal descriptors here for the different levels. As always, though, what's considered low, moderate, or high in one field, like education or psychology, might not be considered low, moderate, or high in another field, like physics. So always consider the context. Although in this case, because we're down there pretty low, we can be pretty confident there's not a lot of a relationship between these two categorical variables. Let's move on to the test of homogeneity. So the setup for that one is, in this case, we have two separate samples and one variable. So that would look like this. We have two samples with one variable. So there is our sample 1 and sample 2, or group 1 and group 2, with the variable in the column, and our same 2 by 2 table. So let's look at an example on that. Your question here is, do football players incur more knee injuries playing on artificial turf compared to natural grass? To answer this, you obtain two separate random samples. Players who practiced on turf only and players who practiced on grass only. So you can see the necessity here for this type of sampling process, because if you have players that are practicing on both turf and grass, it's hard to separate the two. So here we need two separate groups. You then classified the players for knee injury, yes, no. So there's your categorical variable there that's in the column. Based on your sampling and your question, you're going to be using the chi-square test of homogeneity. So for that test, there's a little bit more of a stepwise process. So for the TOH, the chi-square acts as an overall test. Step 1. Perform step 1 to get a general picture of the results. Then you go to step 2 and conduct a comparative test. A comparative test, those tests include Z and T tests for proportion differences. Odds ratio can be used, and a relative risk or risk ratio can also be used. In this type of analysis, you usually set up the 2 by 2 table to compare the row proportions and or to interpret the risk ratio, which I'm going to talk about more, or the odds ratio with respect to the row 1, column 1 category. The comparative test for this example I'm going to use will be a risk ratio or relative risk. And the reason why is because the example involves injury. And when you talk about injury, it's injury and risk kind of go together. So because injury risk is a common way to communicate, injury hazard. So we will use a risk ratio. We're also going to use a risk ratio, as mentioned in the middle rectangle here. Risk ratio is a type of effect size. It's a relative type of an effect size, but we can also use another one that gives us a direct comparison of the two proportions. And so the effect size for the test of homogeneity. So the chi-square, as before, does not indicate the magnitude of the difference between proportions. This is the job of the effect size. For the TOH, we will use a relative measure, which is the risk ratio, and an absolute measure of effect size. The risk ratio and Cohen's H. So the risk ratio, or relative risk, quantifies the relative probability of an event or outcome happening in one group compared to another. And Cohen's H measures the population magnitude of the difference between two independent proportions. And that's exactly what we have. So let's take a look at the analysis for that. So we have a screenshot here back again in Jamovi. So if you look over to the left, you see the two variables here are the setup. So on the first one, I have the surface, which will define the two groups. It's either turf or grass. And then the second variable is injury. It's either injury or no injury, as I have right here. So on this one, again, we're not going to use ESCI. We can simply stick with the frequencies under the analysis tab in Jamovi. That gives us our contingency table dialog box. And as before, we simply put the two variables in the appropriate places. Surface for the rows and columns for and injury for the columns. Then I go down here and check chi-square, and I can also come over here and hit relative risk for the comparative measure. Cohen's H, if I'm not mistaken, is not offered here, and that would have to be computed separately. So then the results will come out over here. I'm showing as a picture on the right, and there's the relative risk here. So I've copied and pasted those tables onto the next slide. So let's take a look at it. So there they are right there. So let's go down here. We'll go through it and then go through an interpretation. So you can see we have our two groups here. So surface, there's our turf group, there's our grass group defining the two rows. And then the variable injury on the top here for the column. Injury, yes, no, for knee injury. So we have 18, 11, 8, and 20. That gives us a row total of 29. For a row 1 turf, a grass total of 28. For a total of 57. So we had 57 actual participants in this study. Then if you go down to the middle table here, as before, we see you have the chi-square statistic. Value there is 6.44. Note that that's quite a bit above the 3.84. And then 1 degree of freedom again. And the probability of obtaining that statistic, a value of that statistic, as large as 6.44 or larger, assuming that the null is true, that there's really no difference between turf and grass on knee injuries frequency, is fairly rare, about 0.01, okay, 1 in 100. And then our comparative measure down below here is the risk ratio of 2.17. Okay, so that tells us that the risk for knee injury on turf is about twice that of what it is on grass. I also have that confidence interval there. Okay, so the lower end is 1.13 and the upper end is 4.17. And one thing to note is that the null for the risk ratio is a value of 1, because the risk ratio is computed as a ratio, which I'm going to show you in a second. And if the risk for each group is the same, we have the same number divided by a value that's the same. So the numerator and denominator are the same. And so you end up with 1. But let's go back up to the top for just a second, and we can kind of take a look at it. There's the like I just mentioned, the risk ratio or relative risk null is 1, implying equal risk between the two groups. There's our group 1, group 2 with our variable 1 injury for our test of homogeneity. So how is that risk ratio computed? Well, that's where the proportions are coming in. So in the numerator here for the risk ratio, we are going to take the value of 18 divided by 29. That's going to give us proportion number 1. And then we're going to take the value of 8 divided by 28. That's going to give us proportion 2. And we're going to simply divide proportion 1 by proportion 2 to get our risk ratio. So let's go through and show you how that is computed. I'm pulling that out. I'll go through it in a second here so you can get the terminology. And as you can see, the value in the table is exactly what you get if you do it just on a calculator. So let's go through that. The risk ratio then is going to be the proportion. So the value in cell A divided by the row 1 total, which is 18 divided by 29, and divided by the value in cell C divided by the row 2 total, 8 divided by 28. And so that can be interpreted then probability-wise. So this would give us the probability of a knee injury of A for row 1 divided by the probability of a knee injury C for row 2. And that can be interpreted as turf injury risk divided by grass injury risk. And there's the math, 18 divided by 29 divided by 8 divided by 28 gives us the 0.62 divided by 0.29-ish, and that gives me a 2.17, essentially about 2. So we end up with a risk ratio of 2, indicating that the risk of knee injury on turf, given the data that we have, is about twice that of grass, with a confidence interval ranging from 1.13 to 4.17. Let's interpret that now. So let's go over here and interpret this. Under the null that O and E frequencies are equal, a chi-square of 6.44 is a relatively rare event. This result provides probability evidence against the null. And the reason why is because we know that 6.44 is quite a bit larger than the critical value of 3.84. That value of 6.44 is only going to occur about once every 100 random samples in a random sampling process. That allows us then to state probability evidence against the null. Comparative analyses show that injury risk is higher on turf than grass. The turf to grass risk ratio of 2.17, confidence interval 1.13 to 4.17, indicates that players have about twice the risk of injury on turf relative to grass. And Cohen's H is equal to 0.69. Okay, and that's a value that's moderately large then for Cohen. And the confidence interval there is 0.42 to 0.95. This indicates a moderate population level injury risk difference between the two playing surface proportions. So we've got quite a bit of evidence here that tells us that the turf injury risk is greater than the grass injury risk. So the findings therefore provide chi-square probability and effect size evidence of a meaningful increase in knee injury frequency for football players who practice on turf compared to grass. Now, one thing you want to note on this one is that we want things to match up, meaning that we've set up the table such that we can interpret the risk ratio appropriately in terms of a yes for injury risk, because we're really interested in the actual risk of the injury. So we want to set that up so that the risk ratio has been calculated using sort of our row 1, column 1 response, which is turf yes, as a way to interpret that. And so what we end up with is a situation where the interpretation, the table, and the actual value, they all match each other. they're parallel in terms of writing and calculating. So in this case, the table allows for a R1C1 risk ratio interpretation. And so the table, the risk ratio calculation, and the interpretation, they all match each other. And this is important methodologically when you write your dissertation, any analysis you do for that matter, that things are parallel so people can follow exactly what you're doing there. Everything is coordinated in order. Otherwise, it becomes confusing for people to understand what you're doing. And the last example is the goodness of fit test. The setup for that one is we have one sample and one variable. It would look like the following. Okay. One group, one variable. That's typically a yes, no, for example, or some type of variable like that. Categorical, nominal, level. So we have one homogeneous sample typically and one variable. Let's look at an example for that. You want to know if alcohol use by females at your school is consistent with the U.S. population average. You randomly sample 100 senior high school females on the question of alcohol use. Research shows that in the United States, 50% of female high school students report ever having used alcohol. So given the setup here, you're going to use the goodness of fit test. And by the way, I just threw in the 50%, and that's hypothetical, but by coincidence, it just happens to be close to the national average. So here's the setup here. Pretty simple. We have females, alcohol use, yes, no. And you want to know if the sample that you have is consistent with the population average, or if maybe for some reason, whatever that may be, the alcohol use is way lower or way higher than what we see in the United States as a whole. So this test, the goodness of fit, in other words, does your response frequencies fit the national average frequencies? So the chi-square goodness of fit is the nominal level equivalent of a one sample t-test with a hypothesis test. Because if you remember in the one sample t-test, you're looking to see if the mean on a continuous numerical variable, if the mean of your sample is the same or potentially statistically different from a population mean. And so in this case, since we have frequency data, instead of using a t-test, we have to use a chi-square, and we would use a chi-square goodness of fit. The chi-square acts as an overall test, step one. Do step one to get a general picture of the results. Then do step two and conduct a hypothesis test to evaluate the O, the observed frequencies, against the population frequencies. The hypothesis test can be judged in several ways. It can be judged using a Z or T test for proportion differences. So in this case, you usually test the proportion in the first cell against the population proportion. So just like we did with the goodness of fit test, where we were looking at injury risk, we want to kind of look at it in terms of injury yes as our set point to interpret the risk ratio. In this case, we want to look at the frequency responses in the yes category against the yes responses at the population level. As before, in terms of an effect size, so the chi-square does not indicate the magnitude of the difference between two proportions, like we mentioned before. This is the job of the effect size. So for the goodness of fit, we can use Cohen's H. Cohen's H. which measures the population level magnitude of the difference between two independent proportions. I recommend using Jamovi and ESCI for a GOF analysis. Let's take a look. So in Jamovi, we have the analysis tab as I've shown before, and we have our frequencies over here. We have our group and our alcohol. So we have our group is sort of redundant here in the sense that we really don't necessarily need the group because it's all females. There's no distinction between males or females. So that really doesn't come into play. The computer is not going to need that because it's all females. And then over here, we have yeses and nos. So to do the analysis, go to frequencies and go to goodness of fit test. And then the next thing you do after you've gone to goodness of fit test is just put the alcohol in as the variable. Now, since we're going to do a hypothesis test, you can come down below here and you can put in the proportions that you want to test against. And so in the population, since the national average was 0.5, we would put in 0.5 as our yes, no category. Because it's 0.5, they're both going to be the same, of course, because proportions would add up to 1. So we're testing our data against this 0.5, and then you get the results over here on the right. So there's our goodness of fit test. And then in ESCI, you can go to the ESCI tab and go to proportions single group. And that will give you a set of results. Put the alcohol into the outcome variable as before, and then you get your results over here on the right. So in this case, we're going to look at both because ESCI has some features that we can use for this particular analysis. There's also an estimation figure that will come up, and if you scroll down on that prior dialog box, you can also put in the 0.5 for your hypothesis test, and once you do that down below here, that allows you to get this estimation figure that you see over there on the right. So then, just like we did with Jamovi, you can put in the evaluation against the 0.5, and that'll allow you to get this figure over here on the right. Now, in the output, I'm not going to show the figure because the table basically does the same thing, but you can also get that. So let's take a look at the results on this one. So up here with the Jamovi, we have our goodness of fit test. There's our results for our sample, which you can see we have 46 and 54. So what do we have? We have 100 there. So 46 divided by 100 would be 0.46, and 54 divided by 100 obviously is 0.54. We get a chi-square value of 0.64 with 1 degree of freedom again, and the probability of obtaining a statistic this large or larger, assuming that the proportion of yes in our sample is the same as the population proportion, there's about a 42% chance of getting that, which is a fairly common situation here. And also note that the 0.64 is well below the critical value. And then in ESCI, the ESCI will give you the same information, but it also gives you the confidence intervals, which are very nice to have. So for the proportion yes, 0.46, we range from 3.7 to 5.6. If you remember, we're testing against a value of about 0.5. And so you can see it looks like 0.5 is still somewhat of a plausible value here. So if we do the hypothesis evaluation, The effect here of yes, the population and the sample. The null is 0.5, that's the population. The 95% confidence interval for our sample is 3.7 to 5.6, as shown above. You can see that basically 0.5 is in that confidence interval. So the answer to that question is yes. And then we can evaluate the two proportions here. We're evaluating the 0.5 against 0.46 to see if those two are statistically different or if they are not. And again, with this confidence interval showing that 0.5 is in our interval, we would predict that they are not. We can use a z-test for that, which is essentially like a t-test, only using a slightly different type of distribution. Our z there is 0.79, and the probability of obtaining a z of 0.79 or larger, assuming that our yes frequency and our population frequency are the same, is about 43% of the time. So in this case, we would fail to reject the notion that our sample proportion and our population proportion for alcohol use with females is the same. Okay? So we're going to fail to reject that hypothesis. So let's interpret that here. Oh, and then before, real quick, just before, there's the little calculation for the Z statistic that will calculate the difference between two proportions. So this is a comparative test for the difference between two proportions, along with Cohen's H as the effect size. But you just take the two proportions in the numerator minus one another, and then you divide that by the standard error of the difference between two proportions. And in this case, we end up with a z of 0.79, which is below a critical value for that, which in this case would be 1.96. So we're going to fail to reject the notion that they're the same. So let's interpret that. There's a 42% or less chance of obtaining a chi-square of 6.64 or larger. Thus, at alpha 05, or the 0.05 level, and assuming the null is true, 0.64 is not a statistically rare event, meaning we're testing our value at 0.05. So we need an event that's rarer than 5%, or as rare or rarer than 5% in order to have some probability evidence against the null. We don't have that. We have a statistic that's going to occur about 42% of the time in a random sampling process. Okay, so this result does not provide probability evidence against the null. The value of 0.5 remains a plausible value of the population proportion, which is pi there, with a 95% confidence interval of 0.37 to 0.56. Cohen's H measures the magnitude of the difference between two proportions in the population. That indicates a small proportion difference at the population level, for which a zero difference remains highly plausible, because the confidence interval for Cohen's H, which is the effect size, also clearly includes 0. So the sample responses are therefore consistent with the known population frequency of 50% alcohol use among senior high school females in the United States. So you can conclude, if you needed, let's say your principal at your school wanted to know this, you would be able to provide them with a lot of evidence that says that the frequency of alcohol use in the senior high school girls at your school is no different than what it is in the United States as a whole. You have 3 lines of evidence there. I have a chi-square probability evidence, Okay. I have a confidence interval evidence. I have effect size evidence. So I have quite a bit of evidence there that all point in the same direction. So if you go back up here though, you look at that and you're like, wait a second, where did this come from? Well, you have to look back at that sampling distribution for the chi-square statistic. Let's take a look at it. So probability on the y-axis, x value on the, the chi-square value on the x-axis. And so there's our critical value of 3.84. And we know already that the value for our observed statistic has to be greater than or equal to 3.84 for us to be in this reject the null hypothesis region. This is the area that provides probability evidence against the null at 0.05. Well, where is our statistic at? It's over here. Our statistic is here, 0.64. And that occurs 42% of the time in random sampling. And so our statistic is in a different zone. It's in this fail to reject the null zone. This is the area that does not allow you to claim probability evidence against the null. And so that's where that first statement in my interpretation is coming from. So this curve and the reject the null and this, what you're seeing here that I just pulled up, this gives us our probability evidence against the null. Then we also have confidence interval evidence, and we also have effect size evidence. So we have 3 lines of evidence here that point to the notion that the frequency of alcohol use for females at your school is essentially the same as it is at the national level. That takes care of that. And I've been very thorough here. And the reason I'm going through this very thoroughly is because there's a pretty good chance that you are going to do a survey possibly for your dissertation, and that you would be using some type of frequency responses to analyze your data, in which case you're going to need to understand how to do chi-square tests, how to work with the proportions, and how to interpret the information correctly. So let's summarize. The chi-square and proportions are analyzed using categorical nominal level variables. The chi-square can be classified into the TOI, TOH, and the goodness of fit test. The chi-square test of independence involves 1 sample and 2 variables. Participants are classified on each variable. The chi-square test of homogeneity involves 2 samples and 1 variable. Participants from each sample or group are classified on the variable. The chi-square goodness of fit test involves 1 sample and 1 variable. Participants are classified on the variable. Typical effect sizes for the chi-square are the phi coefficient for the test of independence, risk ratio, odds ratio, and Cohen's H for the test of homogeneity, and Cohen's H for the goodness of fit test. The chi-square goodness of fit test is the nominal level equivalent of a 1-sample t-test with a hypothesis test. And finally, for the test of homogeneity, set up the 2x2 table to compare row proportions and or interpret a risk ratio or odds ratio with respect to the row 1, column 1 category. For the goodness of fit, you usually test the proportion in the first cell against the null proportion. So if you have any questions about this, there's of course the 5-point analysis quiz. If you have any questions, please feel free to send me an email, and thanks for watching.